In this video, I'm going to show you how you can use calculus to sketch graphs. So we know that e to the power of x looks like this, and when you apply this transformation, it will then give you e. Well, if you apply this transformation, you would put the negative x into here, so that will then become this. Now we don't know what this looks like, but we do know this transformation. This transformation will flip it along the y-axis, so it will look like this. So e to the power of negative x looks like this. So I'm expecting you to know these two graphs. But the question is, what happens when you combine the combination of the two? So our job is to try and understand this graph here, the combination of the two. So we could just cheat and use Desmos, use a graphical calculator to plot this. But in the future, when you're older, you will have to analyze something like this. Let's say you're trying to understand what's going on with a particular point on a wheel as the wheel rotates, moving along here. So when you try and keep track of this point, you will come up with a formula. In the future, when you're older, you will come up with a formula to describe this particular point on this wheel as it's rolling along. So it will give you this thing here, which is called a cycloid, and then you sometimes want to know what's going on. So you want to know what's going on around here. So you could use, well, you would come up with a formula, y equals something. If you use a graphical calculator, when you plot it, it will look something like this. And then if you zoom in, it will look something like this. If you zoom in, it will look something like this. And then if you zoom in further, it will look something like this. And you can never tell what happens around here. Is it really doing this, or is it really doing something like this? If you look at this particle here, by the time it gets to the bottom around here, is it doing this, or is it doing something like, I don't know, let's say something like this? We don't know. You see, by using a graphical calculator, you can zoom in, you can zoom in, you can zoom in. It will always look like this. But if you have an equation, you can analyze the equation and then determine if it's doing this, or if it's doing this, or if it's simply doing this. My point is that a graphical calculator, you can't always rely on it. But then if you look at the equation, you can analyze the equation and get an insight into what's going on. So it's important to be able to understand the equation rather than just jumping to a graphical calculator and sketching it. So let's try and understand what's going on here. We've been given something very strange here. So 0 is always easy. So let's put 0 into the equation, see where it jumps to. So e to the power of 0 plus e to the power minus 0. Minus 0 is just the same as 0. So this is going to be 1 plus 1. So it will jump to 2. So even though you have no idea what this looks like, you can always put 0 in there. 0 is always easy. 1 is another easy one. Let's see what happens when you put 1 in there. E to the power 1 plus e to the power minus 1. We don't understand what it means to have a power of a negative, so we jump to 1 over e to the power of the positive version, and then this will be just the number e. So this thing here will be, well, we turn this into a fraction, times top and bottom by e. So merging these two together, same denominator, it will then give you e squared plus, well, the point here is that it will jump to a number. Who cares what that number is? Let's just say it's somewhere around here. It's just a number. Minus 1 is another easy one to do. It turns out that it will jump to somewhere around here. So something strange like this, at least we at least know this point here will jump to 2. And then if we really want to, we can jump to a calculator, and then it will jump to somewhere around here. So we know the graph looks something like this. It passes through here, here, and here. Now what happens when x becomes very, very big? So let's imagine 1000. What happens when well, not drawn to scale, because from here to here is 1. Just imagine 1000 is here. What happens when x is very, very big, or maybe 1 million, or maybe 1 billion, and so on? Let's just imagine it's 1000. So put 1000 into here, and put 1000 into here, and see where it jumps to. So e to the power of 1000 plus e to the power of negative 1000. So this thing, we don't understand what it means to have a power of a negative. So we would jump to 1 over e to the power of 1000, and then here you've got e to the power of 1000. Don't forget, e is 2.7 something, but let's just imagine it's the number 3, round it off, roughly 3. So let's just imagine this is the number 3. Let's just imagine it's number 3. So this y here, y equals this. So you've got one block plus another block. You see, this block here is going, well, this is going to be a very, very big number. 1 divided by a very, very big number. This is going, the whole block itself will be very, very, very small. This block here is going to be very, very, very big. So very, very big plus very, very small, the combination of the two will be very, very big. Because it's like me saying, you've got $1 million, and then here, this is very, very small. Add $1, then the combination of the two would be a very, very big number. The point here is that when x is very, very big, the combination of the two would be very, very big. So we know it's going to be something very, very big up here. So let me clean this up. So we know it passes through here, 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 and then when x is very, very big, it will jump to up here. And then you can use the same argument for negative very, very big. So when you put negative very, very big in here, it will then become e to the power of negative big, and then plus a negative of a negative, so that would be a positive 1000. Use the same argument. This thing here turns out to be very, very big, so it would be very, very big. So now we suspect that our graph looks something like this. It looks something like this, so we can guess, well, it must pass through this, 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 and this. So a reasonable guess would be that the graph would do something like this. But how do we know that the graph doesn't do something like this? How do we, oh, hang on, badly drawn this bit. Where that? Well, how do we know that the graph doesn't do something like this? It wobbles. How do we know that it is actually doing a straight line as opposed to wobbling? So the way you can detect if it wobbles is to look at the gradient of the graph. So hang on, let me clean this up. So if it truly wobbles like this, then there's a gradient of 0 here, a gradient of 0, 0. There are lots of gradients where it would be 0. So the way to detect the wobble, whether or not it wobbles, is to differentiate it. So hang on. So let me just clean this up. So the way to detect whether or not it wobbles is to differentiate it. Hang on. So let's differentiate this. So look at dy by dx. When you differentiate this, it will just become e to the power of x. When you differentiate this, it will become, it will be the exact same thing, but then you times the derivative of the bubble itself, which is minus 1. But then let's stick a minus. Well, when you differentiate it, it will give you this. Okay, so let me just clean this up. It will give you this. So now, to detect whether or not it wobbles, hang on. So it could be doing this, we just don't know. But if it's truly doing this, then you can see that here the gradient will be 0. The gradient would be 0. There are lots of points where the gradient will be 0. But if you look at the gradient graph, dy by dx, this thing here turns out to be never, this thing here turns out never to be 0, because if you look at this region above 0, when x is above 0, when x is above 0, when x is above 0, this thing here would never be 0, because notice that on the right hand side is always bigger than the left hand side. Just bear that in mind, okay? So when x is positive, when x is bigger than 0, this thing here, well, hang on, when x is always positive, so let me just turn this into a fraction, 1 over e to the power of x. So you got one thing, take away another thing. When x is positive, this block here is going to be smaller than this block here, because if you think about it, e to the power of negative, that's this bit here. This region here will always be smaller than this region here. So this block here will always be bigger than this block. Well, if this block is always bigger than this block, then the whole thing will always be positive, meaning the gradient will always be above 0. So if the gradient is always above 0, it means that the graph is always climbing. And this thing here will never be 0. So we know it doesn't wobble, because if it wobbles, then you know that there's a gradient of 0, 0, 0. Because you know that this thing here is always it's never 0, and it's always above 0. So you know it will never wobble, and then it's always climbing. If it's always climbing, then it's always going up, 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 because the gradient is always climbing. And then you can use the same argument on this side. It turns out that when x is negative, it's always going downhill, downhill. It will never have a gradient of 0, so it will never wobble. So it's always, the gradient is always negative, so it's always going down, going down. When it gets to beyond 0, then it will always be climbing, always climbing, always climbing. So it turns out that your graph will always do this, and it will never wobble. Okay, so it turns out that this graph will look like this. Okay.